Hi everyone, in this video we'll be looking at the chapter of the periodic table. This chapter pulls together knowledge that you have learned before from various chapters and therefore serves as a very good revision and also for you to see the links between different topics. Do you know how the elements are arranged in the periodic table? If you look at the top number, which we call the proton number, do you notice that they are all in increasing numerical order? So as you go across and down, the elements are arranged in increasing proton number. Take a closer look at the periodic table. Am I also right to say that the elements are arranged in increasing relative atomic mass? Yes or no? Okay, if you look closely, you will notice that element number 18, which is argon, has a relative atomic mass of 40, while the next member, potassium, has a relative atomic mass of only 39. Okay, so it's not correct to say that they are arranged in increasing relative atomic mass, but they are arranged in increasing proton number. This is because of the existence of isotopes. So different elements, they have different isotopes, therefore the relative atomic mass, the average, may differ. You will also notice that there are elements with a dash in terms of their relative atomic mass. These are elements that have no stable isotopes. For example, technetium is actually a man-made element. In lower side, you also have learned that there is this step line that divides the metals and non-metals in the periodic table. Those on the left are what we call metals, and those on the right of this line are non-metals. We are going to focus on a few groups of elements when we study this chapter, so you need to know their names. Group 1, we call them the alkali metals. Group 17, we call them the halogens. Group 18, the noble gases. And the group in between, we call them the transition metals. Elements close to the step line have properties of both metals and non-metals, and they are given the name metalloids. In the periodic table, the vertical columns are known as your groups, and your horizontal rows are known as your periods. And there are a total of 18 groups and 7 periods. You may wonder, what does this actually mean, and why is there 2 rows of elements at the bottom? Are they actually connected to the periodic table? So it's quite interesting. This part here actually tells us that the entire block is supposed to fit into this region because there's actually no space to put it on the periodic table itself. Here's what I mean. If you were to expand the periodic table, it will look something like this at the bottom. It is still in ascending order of proton number, but that entire block actually fits right in the middle there. Let's go back to the topic of atomic structure. You will know how to read and write electronic configurations by now. Not sure if you have ever noticed a pattern in the way electronic configurations are written. You can actually derive the electronic configuration of the element from the position in the periodic table. For example, if I'm interested in sulfur, if I were to go across in ascending order, that would be a 2, 8, and then 1, 2, 3, 4, 5, 6, 2, 8, 6. Okay. If I'm interested in the configuration of nitrogen, then it will be 2 for the first row, and then 1, 2, 3, 4, 5. Importantly, group 1, you have 1 valence electron. Group 2, you have 2. And those 13, 14, 15, 16, 17, 18, that will be the last digit of the group number. You have 3 valence electrons, 4, 5, 6, 7, and 8. Take note, for group 18, the exception would be helium, where the first shell can have only a maximum of 2 electrons. Next, look at the number of numbers in the electronic configuration. If there are 4 numbers, it will mean that it is in period number 4. So it's quite easy to do electronic configurations if you understand how to read the periodic table. So what about ions, right? The charge of the ion is actually related to the number of valence electrons. So we say that metals lose electrons to form positively charged ions. Since those in group 1 have 1 valence electron, they form the ion with a plus charge. For example, lithium ion, sodium ion. Those in group 2, they form ions with a 2 plus charge because they have 2 valence electrons that can be lost to have a fully filled valence shell. Okay, then we have 3 plus, 3 minus, 2 minus, and minus. Non-metals gain, metals lose electrons. Another feature is that your non-metals can also share electrons, so they can do ionic and covalent bonding. So with that knowledge, it relates to chemical bonding. And therefore, if I ask you to tell me what is the compound form by a particular element, the formula of it, you are able to predict. So if I ask you, what is the formula of the oxide of sodium, you straight away will know it's Na2O because sodium forms the +1 ion. Then oxide, you know, is the 2- charge ion. Whenever you see same number of valence electrons, you know that they have similar chemical properties and therefore undergo similar kind of reactions. So in the periodic table, we have metals on the left and non-metals on the right. And going across, you have an increase in the number of valence electrons, correct? So we describe this trend as going from having a metallic character to having a non-metallic character. What does metallic character mean? We say that metals lose electrons, so the more likely you are to lose electrons, we say that you have a very high metallic character. We say that non-metals, they tend to gain electrons, so the more likely you are to gain electrons, we say that you have a non-metallic character. So the metallic character actually decreases across the period, while the non-metallic character would increase across the period. What about down the group? Do you think metallic character increases or decreases down the group? So if you look at lithium, sodium, and potassium as we go down, of these three, who is the most likely to lose the valence electrons, and why do you say that? Going back again, everything relates to electronic structure, right? So going from lithium to sodium to potassium, you have an increase in the number of electron shells. What happens when you have more electron shells? Your valence electron is further away from the nucleus. And what happens if it is further away from the nucleus? What kind of forces of attraction do we have between the valence electrons and the nucleus? This is electrostatic forces of attraction. Why? Because your nucleus is positive charge and your electron is negative charge. So oppositely charged particles, they have electrostatic forces of attraction. And as you go further away, this attractive force will get weaker and weaker and more likely to lose the electron. You can think about it as I have my wallet. If it's close to me, I'm less likely to lose it. If I put it far away, it's more easily stolen, right? So the further away the valence electron is from the nucleus, the more easily it is lost, or you can say less energy is required to remove that electron. So if potassium loses electron very readily, we say that the metallic character is very high. Metallic character increases as you go down. And your non-metals, they tend to gain electron, right? The more easy it is for me to take an electron in, the more non-metallic I would be. So between fluorine and chlorine, let's just look at two. Who is more likely to gain the electron based on what we have just shared? The difference is that fluorine has 2 electron shells while chlorine has 3. So if there's an electron that is coming in, who is going to be more attractive towards the electron? It will be fluorine because the shell that this electron is going into is nearer the nucleus. So the electrostatic force of attraction will be stronger. Fluorine will more likely gain the electron, so fluorine is more non-metallic. So there is this concept known as electronegativity, which is not in your syllabus, but you can go and read up about it. It measures the tendency of an atom to attract electrons in a shared pair towards itself. Okay, so this is a summary of what we have discussed just now. You can refer to the bullet points for some of the keywords and phrases. This table takes us back to chemical bonding, where we say that metals, they have a giant metallic structure. For silicon, giant covalent, and then your non-metals have a simple molecular structure. And for your group 18, they are monoatomic, they do not form bonds with other elements. As a result of their structure, it relates to their properties. And then in the chapter of acids and bases, we talk about oxides, right? Metal oxides are basic, non-metal oxides are acidic, with some exceptions. Zinc oxide, aluminum oxide, and lead-2 oxide, they belong to the amphoteric group, whereas your CO, NO, and H2O, they belong to the neutral oxides. But if you look in general, your oxides will go from basic to amphoteric to acidic. Elements between your metals and non-metals are called metalloids, in which they have properties of metals and non-metals. So I actually went online and bought a piece of silicon wafer, which I'll take out and show you. So one look, you may think that it actually is a metal because it's shiny and it has this kind of metallic sound to it. Okay, it does conduct electricity slightly, which is why we call it a semiconductor, but yet not very well, so it can't totally be a metal. Since it conducts slightly, it is also not really a non-metal. So it has properties of both metals and non-metals, and therefore it sits somewhere in the middle of the periodic table. Silicon also forms polymers, and the polymers are actually called silicon. Okay, you might probably heard of the material if you do baking. Let's take a look at some questions over here. You may want to pause the video and try them in your notes first before I go through the answers with you. So question 1, which cannot be predicted? The answer is B, because we cannot tell the number of isotopes based on the location of the periodic table. It's unique to every element. The formula I can tell based on the number of electrons that will be gained, lost, or shared based on the number of valence electrons they have. Okay. Acidic or basic nature we can tell because from the left we have your metals, then non-metals. So it goes from basic to amphoteric to acidic. Okay, so likewise, D also can. Question number 2, the correct answer is A. As you go across in the same period, the atomic number increases. Question 3, they react by losing electrons. We know they are likely to be metals. They all have the electronic configuration 2,8, which means that before they lose the electron, they must have one additional shell with a certain number of valence electrons in there. Okay, this means that they must be in the same period. And this is period number 3. Question 4, they are in the same period of the periodic table. So X forms an acidic oxide and non-metals form acidic oxides, so it should be somewhere on the right. Y forms a basic oxide, so metals form basic oxides, and then Z forms an amphoteric oxide, so it should be somewhere in between. So the order of it should be Y, Z, then X. Here's a question involving some data. So in your group 1, your +1 ion, we are talking about lithium, sodium, and potassium. So after losing that valence electron, your number of electron shell decreases by 1. For your non-metals, after you gain an electron, the number of electron shells remain the same because you just complete the valence shell. The unit PM here stands for picometers. 1 picometers is actually 1 times 10 to the power of minus 12 meters. So it's a very small number. The atomic radius is a measure of the size of the atom, which is also related to the number of electron shells it has. So the trend is that going down the group, the atomic radius increases. Okay, so what does the data tell us? The data tells us that the number of electron shells increases. So as the number of electron shells increases from 2 in lithium to 4 in potassium, the atomic radius increases from 152 to 227. So let's describe the change in radius first. So the radius decreases from 152 to 68. As the lithium atom loses 1 electron, the number of electron shell decreases from 2 to 1. Include a diagram showing the arrangement of electrons. We have lithium like that. Make sure you label. Lose 1 electron to form the lithium ion plus. Okay, so part D, strontium is in group 2. We know that it loses electrons. You can look at the trend here, going from the atom to the ion, the value decreases by about 90 thereabouts. So you're going to find a reasonable value in the range of maybe 100 plus to 120 plus. Okay, so anything within the range plus minus is alright. Remember your units. So when it loses 2 electrons, you're going to lose 1 valence shell, which results in a decrease in the radius by about 90 picometers. I'm not sure if you are wondering why the value here actually increases even though your number of electron shells remain the same. You may want to think about it. Okay, but I'll just give you a rough overview. Fluorine has 9 protons, right? And it has 9 electrons. The protons are positive, electrons are negative, they attract each other. So when you form the fluoride ion, okay, you still have 9 protons, now you have 10 electrons. What happens? When that 1 additional electron joins in the party, there's going to be electronic repulsion. That means the negative charges are going to repel each other. There are more negative charges now than positive charges, and because of that electronic repulsion, the radius actually increases. Okay, and you're going to learn more about this if you're going to take JC chemistry. Okay, but that's about the overview that I'll give you, so you have a rough idea of what is going on. As you can see, knowing the trends are very useful as it allows us to make predictions. So I hope that this video has given you a good recap of all the things you have learned before in the other chapters. I'll see you all in class.